In Chapter 8, we'll study eigenvalues and techniques around the QR factorization. We'll start with the power method, which is a simple eigenvalue algorithm finding a single eigenvalue. Then we'll study QR factorization. Finally, we'll consider QR iteration to get all eigenvalues and eigenvectors at a time. Section 8.1, Preliminaries. And here we'll start with norms of vectors and matrices. The first definition is about inner product or dot product for two vectors having the same dimensions. We can define the dot product, and we are using this dot notation, or U transpose V. Then now here we multiply the entries component-wisely and add. So that is the definition of dot product. Length of a vector is non-negative scalar, and V along with this 2-bar notation, and that is defined in this way. And here that is the square sum and square root, and sometimes it's called the Euclidean norm. For two vectors U and V, we can find the distance between the vectors. It's defined in this way. Here the difference, and we measure the length, and that is called distance. Two vectors are orthogonal when their dot product is 0. That is definition. Once two vectors are orthogonal, then it is satisfying this Pythagorean theorem, and you can easily see it. Okay, we have a vector U, and for example, another vector, so that and V is orthogonal to U. Then now U plus V is U, go here, and from the end of U, you are making V, so that will be here U plus V. Now, once it is orthogonal, then that is a right angle, and from high school, you already know that Pythagorean theorem is for only right triangle. Once this is a right angle, then here length squared plus this length squared must be the length squared of this hypotenuse. Right? So that is the Pythagorean theorem. Well-known and frequently used formula is this one. Dot product of two vectors can be obtained in this way. The product of the norms of each vector times cosine theta. Theta is the angle between the two vectors. And you may try to solve this example. Now we trying to define norms officially. A norm or vector norm on Rn is a function. A norm is a function, and satisfying these conditions is defined on vectors and dimensional vectors satisfying these three. and that is positive definiteness. Once a vector is non-zero, then is the function applied on the vector must be positive, along with a scalar, the real number, and also scale there, and then measure the norm. Then it's the same as norm of the original one and times the absolute value of the scalar. That is called the homogeneity. And in general, this is a triangle inequality. In each triangle, sum of the length of two sides is always not smaller than the final side length. That is exactly triangle. So here that is called triangle inequality. Once these three conditions are satisfied, then the function is called a norm. Here, most common norms are the p norms. P is from 1 to infinity. Of course, here infinity is defined separately. Now, for each component, its absolute value has power p and summed, and the sum now 1 over p power must be applied. Then that is the definition. Now, infinite norm or maximum norm is just to get the largest one in modulus from the entries. Here we have two frequently used p norms. One norm is a power 1 and 1 over 1 power, so that eventually we have this form, the summation of absolute values. That is one norm. Two norm is the well-known Euclidean norm. Once there's no subscript here number, then we consider it just a Euclidean norm. One may consider the maximum norm as the limit of p norms as p approaches infinity. Okay, let's see the solution very simple way. Now here, for example, we consider only three components, a vector in R3, so that here x is now x1, x2, x3. Okay, for that one. And p norm is now x1, absolute value, p power, and x2, absolute value, power p, and x3, p power, and whole summation 1 over p. Right? That's the definition of p norm. Now, we assume one of them is the largest. For simplicity, let's say the x1 is largest in modulus, so that in absolute value, that is the largest one. Right? Assume. You can assume other entry the largest. It doesn't matter. x1 is the largest one. Then here, as p increases, that one is relatively much faster increasing. You may consider this one in this way. Now, this one is x1p here, and then now 1 plus x2 over xp, x1, and p power, plus x3 over x1, now p power, and then here 1 over p, right? So x1p is factored out, and we put on the bottom here. So these are the same. Now, as p increases, here these are x1 is largest, so that is less than 1, so it is approaching to 0. Also, it is approaching to 0. So eventually, as p increases, we may ignore this portion and that one. Then that is exactly now p power 1 over p, so that it is like x1 absolute value. In the beginning, we assumed that is the largest one, so that is exactly now the x vector, the maximum norm, right? So the infinite norm can be considered as the limit of p norms. Here we have Cauchy-Schwarz inequality for the dot product. Its magnitude is bounded by the product of each the two norm of the vectors, and it's written this way, and that portion is Cauchy-Schwarz inequality. Of course, here from earlier formula, for example, here, and now the dot product length, the absolute value of this one is bounded by this product, and cosine theta is between -1 and 1, so that this one cannot be larger than this product, right? But actual Cauchy-Schwarz inequality is this portion. But in definition, this is the same as that one, and that is the same as this one, so we will recheck this. Okay, the sequence of vectors converted to x with respect to L infinite norm, if and only if each component is converting to the each limit. So in FL infinite norm sense, once a sequence of vectors converges to a vector x, then each component will converge to the limit. So that is the theorem says. So here, for this sequence of vectors, as k increases, now that one is always 1, so the limit must be 1. Now 1 over k will converge to 0, so that this one will converge to 2. And for this term, now 1 over k squared, as k increases, it will convert to 0, and point wisely, element wisely, you can consider in this way. Now, sine k will also be oscillatory. However, e to the minus k will converge to 0, so that this whole thing will converge to 0. Okay? So we reject this one. Okay. For norms defined on n-dimensional, finite dimensional space, we can consider this equivalence. L2 norm and L infinite norms are equivalent, which means that, for example, this inequality says that now in L2 norm is converging, for example, approach to 0 and the sequence of vectors. And then in L infinite norm, because of this inequality, once this approaches 0, then in L infinite sense, again, it is approaching to 0. Now, if L infinite sense it is approaching to 0, then even though we have this scaling factor, if it is going to 0, then this must be going to 0, right? So that one norm, in one norm, it is converging to some limit, then along with some other norms, and it is also converging to the same limit. So that is the meaning of equivalence between norms. And we consider here only L2 norm and L infinite norm. However, L1 norm also, they are all equivalent because it is defined on finite dimensional space. Okay. Now, mapping norms. Mapping norms are natural expansion of a vector norm. And a vector, okay, for metric, now metric A has dimension m by n, so we consider as R, m by n. Then it has m times n entries, so that a metric norm can be considered as a norm defined on m by n dimensional space. So it's a kind of vector norm on the mn dimensional space, again, so that it should satisfy the similar three properties. So it's positive definiteness. For non-zero, it's always larger than equal to 0, but here, when A is 0, the matrix is 0, all entries are 0, then it's 0, except this case is always positive. And scaling, coming out with absolute value, and also this triangle inequality, so that similar three properties must be satisfied to be a metric norm. This is the Frobenius norm, which is just direct expansion of L2 vector norm for each entry, the square sum for all entries, and then half power. So it is a direct expansion of L2 vector norm, which is called Frobenius norm. Now, another family of metric norm is called operator norm, or induced metric norm, or subordinate norm. That is defined in this way. We consider first a vector norm. Once AX is obtained, then it is a vector. A is a metric, but a vector X is multiplied, then that is a vector. So we can measure by using a vector norm. The same vector norm will be used to measure X, the length of X, and the ratio, once A is non-zero, and among all possible X. Now try to get this ratio maximized. Then the quantity is the metric norm in the same sense. Once you start with, for example, L1 norm, and again L1 vector norm, then we say this is L1 metric norm. L2 norm, then we say is L2 metric norm, and so on. Okay, in this way, we define metric norm induced from vector norm. So we say the norm is the induced metric norm. Here we have a theorem showing properties for all operator norms defined in this definition, and the Frobenius norm here for all the norms. These inequalities are satisfied quite simple, like Cauchy-Schwarz inequality. Now here a one norm is metric one norm. By definition, it is this one, maximum of this quotient. Now, top and bottom are measured by using L1 vector norm. That is the definition. But for this quantity, it's not easy to figure out. So we need some computational the formula that is exactly this one. Now, for every entry of the matrix, take absolute value, and summation is I-directional summation. So a vertical summation. Okay, let's visualize it. For entries, first take absolute values, and vertically we add these entries. Then each column will produce a quantity like that. Then among these quantities, we try to choose maximum. Now, in J direction, horizontal direction, in metric, the common convention is there's J direction, that is now I direction, right? Okay, so among this one, we try to choose the largest one, which is the same as a one norm. This is a definition. This is a computational formula in some sense. Now for maximum norm, this is the definition. Now this is a formula. For this one here, we try to make J-directional summation, which is horizontal summation of the absolute values of entries, so that each row will produce a quantity. Among this one, now try to choose maximum. So that is same as metric maximum norm. So it is not much confusing. One is vertical, so you are doing vertical summation, and infinite notation is somewhat horizontal, so that you are adding horizontally. So it is quite clear, right? Okay. Now, two norm, that is a definition. Of course, this two norm is metric two norm. This two norm is vector two norm, okay? Definition, but now this is a kind of a computational formula. And after getting a transpose A and find largest eigenvalue, and now here square root. For this metric, the eigenvalues are always real and non-negative, so that you can choose just a maximum of these eigenvalues and square root. And in two norm, here metric A two norm is the same as a transpose two norm. How about for example, one norm and a transpose one norm? Are they same? No. One norm is basically for absolute value, now vertical summation, but transpose vertical summation is the same as, in fact, the L infinite norm, so that if you want to make equal, then there must be infinite norm, then there must be same, right? Okay, once a metric is a normal metric satisfying this equation, then now, of course, to get this equation meaningful, the metric must be a square metric. Now, A transpose A equals AA transpose, and that one will be satisfied for every symmetric matrices. So that anyway, once it is a normal, then the metric 2 norm of the metric is the maximum eigenvalue in modulus. In general, it's not, sometimes it's not real number, or sometimes a negative or complex valued eigenvalues. So after getting all the eigenvalues, now in modulus, the maximum is the metric 2 norm. But for this case, the eigenvalues are all real and non-negative, so that you don't need, for this one, such absolute sign over there. Okay. Okay. A is a square metric in n-dimensional space, n by n-dimensional space. Then we can define the quantization number of the metric, and we are using this kappa notation. Kappa of A is, by definition, A norm times A inverse norm. Once it is not invertible, we may consider A inverse norm is infinity, so that here for singular matrices, we can say its condition number is infinity. Okay. Of course, depending on the choice of norms, now separately you can say the condition number. If you start with L1 norm of A and A inverse, then you can say L1 condition number. Right? Let's see this example. A is given here, and then we have A inverse and A transpose A in this way. Okay, let's try to find the A1 norm, A infinite norm, and A2 norm. Okay, let's start with A1 norm. One is vertical, so that you are adding the entries in modulus vertically. Among them, we are choosing the largest one, so that here maximum of, from first column we have 2, addition is 2. From second column we have 7, and from third column we have 3. So out of these 3 numbers, 7 is the largest one. So A1 norm is 7. Okay. A infinite norm, maximum norm, is now horizontal summation for A over there. First row will make a 4. Second row, again 4. And the final row, again 4. You have to add them, the entries, after taking absolute value. 1 to 1 is 4, 0, 3, 1 is 4, 1 to 1 is again 4. So that the maximum is 4, right? Now, to get a 2 norm, okay, you have to find now the eigenvalues of A transpose A, and choose the largest one and take square root. Okay, let's start with finding eigenvalues of A transpose A. A transpose A minus lambda I. Then, okay, we put here minus lambda, minus lambda, minus lambda, and try to get determinant. Then from, okay, I purposely made this matrix so that these two are 0, and then determinant computation is way simplified. Yeah, 17 minus 3 and oops minus lambda, right? That must be lambda. And here 3 minus lambda and minus. Now 7 times 7 is 49. So it's 49. Okay. That is a characteristic equation. And 2 minus lambda. And then that is lambda squared minus 20 lambda. And that is 51 minus 49. So that is plus 2. And we have to solve this one. Now, if you solve this equation, then from this one, you'll get 2. And by using quadratic formula, you'll get this 2. Okay, that one and this one. And largest one is apparently that one. And then square root of 19.89, that is now 4.46. So here we can say from this computation, here A, okay, 2 norm is, we don't know right now the exact value, but anyway, it's around there, right? 4.46, let's say in this way, okay? Now, how about L1 condition number? Kappa 1A, which must be A 1 norm times A inverse 1 norm. A 1 norm is already obtained to be 7. Now, for A inverse, we have to get 1 norm. Okay, A inverse is given for your convenience. Now, for that one, now that is a scalar multiplication. So in finding norm, you can put scalar outside the same way. And then, now it's 1 norm, so that there's a maximum of vertical summation. Okay, that is 5 from first column. And then from second column, there is 6. From third column, again 5. So maximum is 6. So that along with the now half, so 3. So that is 7 times 3, which is 21. So the condition number in L1 norm is 21. Of course, for infinite norm, you can get the condition number. Let's try to get the condition number in L infinite norm. So here, L infinite condition number of A, which must be A now infinite norm and A inverse and infinite norm. We already know that the first component, okay, over there we have 4. And again, from A inverse, we try to get infinite norm. Again, the scalar, the same way. And then now we try to add the entries horizontally. So first row is making 2, second row will make 4, and final row, that is making 10. Right? So that is 5 and 4. So that 4 times 5, which is 20. Okay. Okay. At the end of the section, we see a theorem which is called Neumann series theorem. A is a square metric, and for any metric norm, for any subordinate norm, here is less than 1, then no matter what it is, and if we satisfy this one, then identity minus A must be invertible, and its inverse, practically, inverse can be expressed in this way. That is same as once K is 0, then it's identity, and now A plus A squared plus and so on, like that. This is mimicking the formula, okay? 1 over 1 minus x. That is same as 1 plus x plus and Taylor series, right? There's x squared plus x cubed plus and so on. But this is only valid when the absolute value of x is strictly less than 1. So once it's not satisfying the condition, then it's nonsense. So exactly over there, once it is strictly less than 1 in norm, then now here it's like almost same form over there, right? And identity minus A inverse can be written in this way. Okay. Okay, this is the end of the section. Thank you.